Okay, in this section we will discuss equipotential surface and the properties associated with equipotential surface, right? So let's start with the equipotential surface's definition. Equi means equal, potential we all are aware of it. So equipotential surface may be defined as that surface at every point of which the value of electric potential is same, that is constant. So equipotential surface, it may be the surface of a body or it may be any surface in space or any medium. But the condition is at every point on that particular surface, the value of potential must be constant. So that will fulfill the condition for the surface to be an equipotential one, right? So there are some very important properties associated with it. First is work done in moving a charge from one point to another point on an equipotential surface is always zero. Let's try to verify this particular fact. This is suppose an equipotential surface. Like this is a point charge and this is a sphere. This is a hollow sphere, right? This is a hollow sphere. So this is point A and this is point B. So point A and point B both are obviously at the same distance from the source charge which is located at the center. So the potential at point A must be equal to potential at point B, each being equal to Q over 4 pi epsilon r. Therefore, these are the 2 points which are having the same potential. So this surface, any part of this hollow sphere at the center of which this source charge is imagined to be placed can be treated as an equipotential surface. So I have taken a small part of this hollow sphere. This is a small part of that hollow sphere. So this is point A and this is point B. So these are the 2 points which are at the same potential. So this surface may be considered to be an equipotential surface. Now as per definition, the potential difference between these 2 points or the influence of electric field due to the source charge is defined as, we will consider A to be the initial point, B to be the final point. So the potential difference between the 2 points A and B is defined as VB minus VA, work done per unit charge. This is any test charge which is to be carried from one point to another point, from A to B. Now look, this is as per the definition of potential difference. We have done it in the earlier section. Now since it is an equipotential surface, therefore VA is equal to VB is equal to V, say, it is constant. So therefore the potential difference becomes 0. So WAB divided by Q0 becomes 0, which implies that WAB is equal to 0. So that's the mathematical verification of the important property that the work done in moving a charge between 2 points on an equipotential surface is always 0. So that's the first important property. Second, suppose this is source charge. The field lines will be like this. It will emanate from the positive charge. The field lines will be like this. So this electric field, it will always make an angle of 90 degree with the equipotential surface. The electric field always makes an angle of 90 degree or it is always at right angle to the equipotential surface. This also we can mathematically justify or verify. So here also we'll make use of an expression which we have earlier derived. So potential difference between the 2 points in terms of line integral of electric field may also be written as, this is the potential difference, it is given by negative of the line integral of the electric field, E vector dot dl vector. Limits would be from Ra to Rb. We have done it, isn't it? Now since Va is equal to Vb, therefore this potential difference between the points A and B becomes 0. This being an equipotential surface, therefore we get E vector dot dl vector is equal to 0. Now the scalar product of these 2 vectors which are non-zero is equal to 0. It is feasible only when these 2 are perpendicular to each other, which simply implies that E vector is perpendicular to dl vector. Dl vector is somewhere over here, between the 2 points where the charge is to be moved on an equipotential surface. So what we have proved is the electric field always is at right angle to the equipotential surface. There are some other important properties associated as well. We will discuss one by one. So let's start with the third one. Third property. Two equipotential surfaces can never intersect each other. It is because if the two equipotential surfaces intersect at a point, then at that particular point of intersection, we may get two different values of electric potential, which obviously is not feasible, because if it is an equipotential surface, then the potential must be constant at every point on that particular surface. So therefore, there is another important property that equipotential surfaces can never intersect each other. It can never intersect each other. Let's discuss some types of equipotential surfaces, like for point charge. For point charge, like this. This is a point charge. The equipotential surface must be in a plane, it is circle. While it is circular, while in space, if the point charge is placed in space, then the equipotential surface must be spherical. So this is an equipotential surface. This is the electric field or electric field lines. It will be perpendicular to the equipotential surface. So for a point charge, the nature of the equipotential surface is spherical in 3D in space, or is circular in a plane in 2D, right? Suppose we discuss for a line charge distribution, for a line charge, straight line. This is the charge distribution, straight line. Here the charge is uniformly distributed. So consider this to be the axis, we can draw a right cylinder. Now this axis, which acts as the line charge distribution, it is equidistant from any point on the surface of this right circular cylinder. Therefore, at any point on the surface of this right circular cylinder, the value of potential would be constant. So as a result, for line charge distribution, the nature of the equipotential surface may be considered to be cylindrical, right? Another very important interesting thing is, for uniform electric field, the nature of the equipotential surface is planar. I'll justify it. What I've stated is, for a uniform electric field, the nature of the equipotential surface is planar. As you are aware, uniform electric field is represented by a set of equidistant parallel lines like this. So, for an equipotential surface, the electric field line should be perpendicular to that particular surface. So, it is possible only when the surface under consideration is planar, like this. This is a planar surface. So this is an equipotential surface. This is an equipotential surface. Now the diagram is more appropriate. It will give a 3D effect. So for uniform electric field, the equipotential surface is planar. So what we will discuss is, equipotential surfaces can be spherical, it can be of cylindrical shape, or it can be even planar. Now there are some other important conceptual questions as well. For that, we need to consider a very important fact, that electric field at a point is negative of the potential gradient at that particular point. This is the potential gradient. So basically, it clearly suggests that electric field is always in a direction opposite to which the value of potential increases. Or in other words, the direction of the electric field is always along that direction in which the value of potential decreases. So in case dV is constant, in such a scenario, electric field in magnitude is inversely proportional to dr. Dr is the separation between the equipotential surfaces. So what it suggests is, or you can write dr is inversely proportional to the strength of the electric field. So what it suggests is, in the region where the electric field is stronger, the spacing between the equipotential surfaces are much closer. While on the other hand, in the region where the electric field is weaker, the value of E is smaller, there the separation between the equipotential surfaces is much larger. So in order to convince this particular statement, let's consider this diagram. Suppose we need to draw three equipotential surfaces in the case of non-uniform electric field. So we'll discuss in case of non-uniform electric field. Two cases may arise. First, suppose this is non-uniform electric field. Let us consider. This is the increasing direction of the electric field. This is the increasing direction of the electric field, right? Electric field is increasing along this direction. Here, suppose it is E1, this is E2, and this is E3. So, E1 is less than E2 and it is less than E3. So, electric field is increasing along this particular direction. So, it is non-uniform. So, we need to draw 3 or 4 equipotential surfaces. So, we'll draw like this. This is the first equipotential surface. This one is the second equipotential surface, and this one is the third equipotential surface. Now, this is suppose dr1, the separation with them is dr2. Now look, these are the three equipotential surfaces. This is region where the electric field is much stronger as compared to the electric field in this particular region. So look, wherever the strength of the electric field is stronger, the value of E is more, then the separation with the equipotential surfaces is lesser. While on the other hand, in this region, the strength of the electric field is comparatively smaller. E is having small values, so dr will be greater. In this case, in this region, the equipotential surfaces, the separation between the equipotential surfaces is much larger. So this signifies non-uniform electric field, and these are the three equipotential surfaces. So they shouldn't be equidistant. The closer equipotential surfaces signifies the fact that in that particular region the electric field is much more stronger, right? There's another example, non-uniform electric field only region. There is another example. If we consider this to be a point charge, we are aware electric field due to a point charge obey inverse to arrow. So as the observation point, its distance increases from the source charge, the strength of the electric field will keep on decreasing. The electric field is spherically symmetrical like this. It is spherically symmetrical. Now, in the case of a point charge, if we are supposed to draw three equipotential surfaces, then it should be like this. As I stated, in plane it will be circular, and in case of space it will be spherical. The separation between the equipotential surfaces will keep on increasing. It will keep on increasing. These are the four equipotential surfaces. This is the first equipotential surface, this is the second one, this is the third one, and this is the fourth one. Now look, here, which is much closer to the source charge, the strength of the electric field is maximum. So here, the separation E is greater, so dr would be less. So the separation between the equipotential surfaces are very, very small. They are crowded. While at a region which is far away from the source charge, the strength of the electric field will be smaller, and accordingly, the separation between the equipotential surface will be larger. So this large separation between the equipotential surfaces is indicative of the fact that in this region the electric field is much, much smaller as compared to the region where the potential surfaces are, equipotential surfaces are crowded. So these are some very, very important diagrams which might be asked in the context of equipotential surfaces.